Okay, here's the penultimate lesson for Essentials of Calculus. I was thinking maybe I should have called it Kitchen Calculus, given the fact that this is all being done in my kitchen. I'll think about retitling it. It might be kind of clever. Anyway, here are some functions that we, as of yet, don't know how to find the antiderivative of. And so recall that this is the notation if we just want the antiderivative. Since the antiderivative is important if ever you want to find the area underneath the curve or something, this is often something we want. So quite often we just want the antiderivative and then you can do whatever you want with it afterwards. So anyway, there's one right there. Do you see any function whose derivative is that? Okay, well, what I'm going to show you right now is called the method of substitution, and it's basically kind of doing the chain rule in reverse. Here's what you do. You look at that and you ask two questions. First question is, what is it that makes that impossible to find the antiderivative of? And the first thing that should come to your mind is, we've got the cosine of x to the fourth. We know what the cosine, if I just had the cosine of x and I asked you the antiderivative of that, that's easy. That's the sine of x. But as soon as you have an x to the fourth in there, that blows that all to smithereens. So no good at all. So that's what's complicating things. The other question you should ask yourself is there some part of that for which the derivative is also there? And you see, oh, x to the fourth, the derivative of x to the fourth is 4x cubed. Well, that's almost there. We're just off by a constant, and constants we don't care about at all. We can factor them outside the integral sign, whatever. So those are the two questions to ask, and they both point to the same substitution to make in this regard. Here's what we do. We let u be equal to x to the fourth, and then the derivative of u, du dx, is equal to what? 4x cubed? Agreed? The derivative of u is equal to that. And then we make use of Leibniz's notation here. He's the one that came up with the du dx. And we write that as du is equal to 4x cubed dx. And the reason this works is basically just because he has this nice notation that allows us to kind of do the chain rule in reverse. So basically we're just kind of doing the chain rule in reverse by doing this process here. So here we go. So now what we do is we need to get this whole thing in terms of u rather than in terms of x. So how do we do it? We have a cosine of x to the fourth. That's going to become cosine of u. So that takes care of this. Now, if we can get everything else in terms of u, we're all set. We have an x cubed dx. Well, notice that x cubed dx is equal to du divided by 4. See that? Du over 4 is equal to the x cubed dx. So in place of x cubed dx, I'm going to put du, there's your du, and divided by 4. I could put the 4 here, but we might as well bring it right out front, like so. So now we have written all of this in terms of u, and now here's a form that we can find the antiderivative of. That's going to be 1/4. What's the antiderivative of cosine? It's just the sine of u plus c. And then once you go ahead and find the antiderivative, then you put it back in terms of the original variable, and you're done. That's all there is to it. And you can always check yourself by taking the derivative of this and seeing if you get this. Let's give it a try. The derivative of this thing is going to be the 1/4. We'll say out front. The derivative of the sine of anything is the cosine of that thing times the derivative of this thing. What's the derivative? The derivative is 4x cubed. And then finally the derivative of c, of course, is 0. So sure enough, the fourth goes away and I end up with a x cubed times cosine of x to the fourth. So you see, as I say, we've really just kind of done the chain rule in reverse. We've kind of undone it. Okay, so that's the idea. That's called the method of substitution. And it's a little bit more challenging than taking the derivative of things, because you have to kind of pick and choose what you think the substitution might be. And of course, it doesn't always work either. So it's one of many methods that are available for trying to find antiderivatives. Let's try another one. This is one of my favorite problems. I came up with this one quite a while ago, and I've put it on tests quite often. There, isn't that intimidating looking? So I look at that, and you say, wow, that just looks horrendous. What can I do with that? And one thing that should come to your mind is, you've never seen anything with a 1 minus ln of x squared in the radical. We've never seen anything like that. So we need to somehow make this simpler looking. So let's just give it a try and see once what happens if we let u be equal to, I'm going to do it down here this time, u be equal to the ln of x. Okay, let's see once what happens. Then du is equal to 1 over x dx. Notice I already did 2 steps in one. I could have written this as du dx is equal to 1 over x and then brought it over, but it's easier just to write the du here, take the derivative, and put the dx right next to it. Okay? So let's go ahead and see once if we can get this all in terms of u now. Okay? So here we go. It's going to be square root of 1 minus u squared. So it's going to be 1 over square root of 1 minus u squared. That takes care of all this. Now, what do I have left? Oops, I'm sorry, I should have had a dx on here. This is where dx's and so on are very important, because the dx turns over into a du. So here I needed a dx. So dx divided by x, notice, is equal to du. So all this stuff right here becomes my du. How nice is that? Okay, now, does that look familiar? Before we're done, though, notice that this is a definite integral. So since this is a definite integral, I need to not only change all this stuff into u's, but I also need to change the limits of integration to correspond to this new variable. So here's what I do. I say, here the dummy variable is x. So I say when x is equal to 1, what's u going to be? When x is 1, the ln of 1 is equal to 0. So I'm going to get a 0 there. Now I say, here the dummy variable is x. When x is equal to square root of e, what's the ln of the square root of e? Well, that's e to the 1/2 power. And you can bring the 1/2 down. 1/2 times the ln of e, and the ln of e is equal to 1. So this is just equal to, or the other way of thinking about it is these two things undo each other. And so you just end up with 1/2. So there you go. So how clever is that? Okay, that's why I made this one up, to be kind of nice. So the only reason you would want to do that is if you already knew what the antiderivative of this thing is. And so this is where you just need to have a repertoire of antiderivatives that you're familiar with. Do you remember what this one is? This is the antiderivative, or I should say this is the derivative. This is the derivative of the arcsine. So the arcsine is the antiderivative of this. If you take the derivative of arcsine, you get this thing. Remember that? So this is the antiderivative of that. This is what you want. So the antiderivative of this is this. And so now we evaluate that from 0 to 1/2. What's the arcsine of 1/2? That's the angle whose sine is 1/2. Well, let me write it like this. The angle whose sine is 1/2, that's pi over 6. And the angle whose sine is 0 is 0. So there you go. Kind of a nice problem. This is one of my favorites. I like it. Okay, kind of a pretty answer. There you go. Tests a lot of things, okay? That's why I like it. Okay, let's try another one. That one was kind of conjured up. This one is maybe a little more typical of kinds of things that you might see. Let's say you have this one right here. I think I want, yep. Okay, so you look at that one and you say, nothing really comes to mind. I don't see anything there whose derivative I also see, not like the last two problems, but it is pretty clear what the problem is. The problem is I've got something kind of messy underneath that radical. I know how to handle this. This is just x to the 1/2 power, and so I know the antiderivative of that is just going to be what? X to the 3/2 times 2/3. So no problem, but as soon as I have that -1 there, it follows it up. So let's see if we can't get rid of that. Let's try to see if we can't relieve ourselves of that little burden. So I'm going to let u be equal to this thing. Then du, the derivative of this whole thing is just going to be 1 dx. Okay, let's see once what happens. This right here becomes the square root of u. Okay. You always have to take care of your dx. dx is just equal to du, so no problem with that. So I've taken care of that as well. The problem is we still have an x there. How can I handle the x? Well, how about this? Look at here. X is equal to u plus 1. So I should have left myself a little more room here. U plus 1 square root of u du. Okay, let's change our limits of integration. If x is equal to 5, 5 minus 1 is 4. If x is equal to 10, 10 minus 1 is 9. So this integral is equal to this one, no problem there. The question is, can we find the antiderivative of this? Yeah, I think we can. Okay, do you see it? This is the same. Let me just save one step here. This is u to the 1/2 power. Right there. So if I multiply it through, it's going to be u to the 3/2, right? This is u to the 1 power. So when you add the exponents, it's u to the 3/2 plus u to the 1/2 all times du, going from 4 to 9. Now we can take the antiderivative. It's going to be what? U to the add 1, 5/2 times 2/5. Dividing by 5/2 is the same as multiplying by 2/5. Here's what? U to the 3/2 times 2/3. So you do all that. You can add c of 0 if you want, just 0. And you integrate from 4 to 9. So remember, you always need to change your limits of integration. So what happens? When you stick a 9 here, the square root of 9 is 3. 3 to the 5th is 243. 243 times 2 is 243 times 2 is 486. So it's going to be 486 fifths plus, when you stick a 9 in here, square root of 9 is 327, 54 thirds. Did I do that right? Yeah, I think so. 3 cubed is 27. 27 times 2. 2 times 3 is 54. 54 over 3, that reduces though, right? 18 it becomes. So that just becomes, let's see. Let me do that one more time. This is, oh yeah. This is 3. This is 9. Square root of 9 is 3. 27. 27 times 2 is 54. 54 divided by 3 is 18. So this whole thing becomes 18. Okay. So that's all that. Now you subtract off when you put a 4 in there. Square root of 4 is 2. 2 to the 5th is 32. 64 fifths. Plus, and you put a 4 in here, and you're going to get what? Square root of 4 is 2. 8 16 thirds. 16 thirds. So I don't care. Should we just? I'll leave it like that. Okay. The bunch of detail work to subtract this stuff off. So that's the idea. Okay. So there's that one right there. Okay. Let's try one or two more just to show you what can be done. Okay. Here's one. How about this one? There you go. Antiderivative of the tangent. By the way, one of my little pet peeves with regard to calculus students, and you'll see that this is really a pet peeve, is that some students occasionally will kind of put in a little extra flair in their integral signs. You don't want that. You don't want ostentation and such. That's no good. More usual, you have some others that are just kind of sloppy with it, just kind of go like that, and it just kind of lacks character. There's no gravitas to an integral sign like that, okay? So you want something which is neither draws attention to itself, but you want it to have some nice character to it. So give it a little bit of a umph like that, okay? So there you go. So there's the tangent, and what's the antiderivative? Well, heck, I don't know, but what I do know is that the tangent is the sine over the cosine. That's the definition of the tangent, so that's not a bad place to start. I don't see what else to do. And now the question is, can I look at that thing and say, oh, I see part of that whose derivative is also there? Well, yeah, I could let u be equal to sine of x, and du is equal to cosine of x. The problem is this cosine is on the bottom. I need the du to be up on top, but I have a 1 over cosine, so that won't work. That won't work, but I can do it the other way around. Let's let u be equal to cosine of x, and then what's the derivative of the cosine? Derivative of cosine is negative sine of x. Agreed? So this thing here becomes 1 over u sine of x dx. If you multiply both sides by -1, you get sine of x dx is negative du. Let's bring the negative out front. Du. And now that, remember, is just the negative ln of the absolute value of u plus c. And now you can substitute back in your u. Like so. And you can either leave it like that, or you can, if you want to, you can bring the negative inside. If you bring the negative inside, it's going to be 1 over the cosine. 1 over the cosine is the secant, recall. So you can write it either way. I always prefer to have things in terms of sines and cosines myself, so I like it like that. Okay? Let's just try one more. Well, actually two more. This one is just very simple, but it's kind of important. What if we have this? Okay, you see that quite often. Could have had sine of x there or something like that. Here's what you do. You just let u be equal to 5x. Du is going to be 5 dx. And so this just becomes cosine of u. Dx, notice, is 1/5 du. And so now that's going to become 1/5. The antiderivative of the cosine is the sine of u plus c. So it's going to be 1/5 sine of 5x plus c. And that's one you could have almost gotten just by thinking about it. You think, well, let's see, I want something whose derivative is a cosine of 5x. I need to somehow alter it so I get a 1 in front there by the time I'm done. So there it is. But that's why we also said the antiderivative of e to the 5x is equal to what? 1 over 5 e to the 5x. You could do it the same way with a substitution. Okay, anyway, let's do one more nice one. This is one of my favorites again, just because it looks kind of simple, but it's a little bit involved. Okay, there it is right there. And you look at that and you say, dang it, what can I do with that? I can't, if I let u be equal to x squared plus 1, du is equal to 2x, but I've got that 1 there and so on. What do I do with that? So again, all these things, if you want to, go ahead and turn off the video, put it on pause, and see, before you watch me do any more writing, see if you can figure it out for yourself. But assuming you've done that if you wanted to, here's what I'm going to do. I'm going to break up the numerator, right? Algebraically, I can do that. And I'll actually even write it as 2 integrals. Okay? So, this one here, now I can let u be equal to this thing. Du, notice, is going to be 2x dx. So this all becomes what? It's going to become u on the bottom. X dx is going to be 1/2 du, so you can bring the 1/2 out front. Du there. Make sure you change the limits of integration. When x is equal to 0, u is going to be 1. And when x is equal to 1, u is going to be 2, right? 1 squared plus 1 is 2. So you're going to get that. So let's go ahead and finish this one up. This is going to be the ln of the absolute value of u from 1 to 2, which is going to be 1/2 the ln of 2 minus the ln of 1. The ln of 1 is just 0. So this is all this part right here. And now, what about this part? Do you recognize it? That is the arctangent of x from 0 to 1, because the derivative of the arctangent is equal to that. And so here, this is going to be the arctan of 1 minus the arctan of 0. The arctangent of 1, that's the angle whose tangent is 1. What's the angle whose tangent is 1? That's your 45 degrees, or pi over 4. And what's the angle whose tangent is 0? That's just 0. So there's your final answer right there. So kind of nice, okay? Kind of elegant. You need to do a little algebra. You need to know your antiderivatives. So very good. So that basically completes all the material for a Calc 1 course, a traditional Calc 1 course. We'll have one more lesson, which I'll kind of review some of the things from the last half of the course since the mid-course review that we had. Okay, very good.